Hey, welcome to section 5.2, where we'll be investigating how to graph polynomials. Um, so unfortunately, graphing polynomials is hard. In the sense that graphing quadratics and all the polynomials, we'll see in this class, you're completely capable of graphing pretty easily. But it's hard in the sense that if we wanted to graph something like x to the fifth plus 3x to the fourth plus 5x cubed plus 1/2 x squared plus 7, we would run into quite a bit of trouble. And you might be thinking, well, why don't I just plug it into Desmos and do that? And yeah, that's exactly how we would approach graphing something like this. Desmos actually uses a pretty dumb way of graphing polynomials. I mean, dumb in the sense that it's the solution that like a high school sophomore would come up with, where why don't we just plug in points to the function a million times, and that gives us a picture of the graph. And that's exactly what Desmos does. It just plugs in a whole bunch of different values for the graph that are so close together that the human eye can't really detect it, and then it connects them. But actually figuring out what the graph looks like from the equation is tough. And the reason why it's tough is when we're graphing, we typically want to have, our graphs should have 3 features. We want our y-intercept, our x-intercepts, and we want end behavior. When you go on to calculus, you'll expand the idea of what you want in a polynomial and the graph of a polynomial to also include local maxes and local mins, as well as something called concavity, where basically does the curve look like this or does it look like that? So calculus gives a foundation to figure out end behavior and concavity. For algebra, we're going to be concerned with y-intercepts, x-intercepts, and end behavior. And then I guess if it's positive or negative between the roots. So maybe in a sense, that's 4 features. All right, so if we want to graph, let's say x cubed plus 5x squared plus 4x, we can find the y-intercept really easily. Let's call this f of x. Then the y-intercept is just f of 0. We always just plug in 0 to find the y-intercept. And maybe take a second to think about why that's the case. We plug in 0 to this function and we get 0 out. So if we put a graph down here, we know that at 0, our y-intercept is 0. And then we have to figure out the x-intercepts, which take a little more work. And that's particularly why graphing something like x to the 5th plus 3x to the 4th and so on is tough, because we don't have a great way to figure out the intercepts. But for this function, we can handle it. We notice that we can actually pull out an x, because each term has an x. 5x plus 4. And then we know how to factor x squared plus 5x plus 4. So take a second to do it on your own. Pause the video and think about it. And hopefully you came up with that x plus 4, x plus 1. So then when we're looking for f of x equals 0, we get that x equals 0, -4, or -1. So then we just put those intercepts on. And this is sort of a skeleton for our graph. Now we want to check what goes on between the roots, if it's positive or if it's negative. And to do that, we can just pick 1 point between each interval. So between -4 and 1 and -1, we'll pick a nice number. Let's pick -2. And then f of -2, and at this point, it's usually easier to work with the fully factored form, is -2 times 2 times -1. And we actually only care if it's positive or negative, and that's positive.